Am I visible to all?
Yes, sir, you are visible.
Okay, thank you
Yes,
very
sir.
much. And what about the slides now? These
Yeah,
are
they are also visible, sir.
okay. Thank you very much. So already we are late, but it's okay. It's because due to some holiday and I got stuck in the work, but it's okay. No worries because I know that a continuous session is already scheduled by 3:30. But we'll try to cover up these 5 minutes also during our session hours. So this is the our second session to be connected with again some hands-on experience that is related to some quantum machine learning details. Okay, so as in the earlier class, we already discussed with the quantum machine learning fundamentals, okay, including data encoding mechanism, feature mapping, okay, and how it is to be used using a kernel function. Followed to that one, we also had a discussion related to our that is a other quantum tools, like if we talk about a quantum memory, okay, or the swap circuit in order to test for the similarity among the quantum states, okay. And uh, followed to that one, we are here in the today's context of expanding our that is or just to continue to be continued with our lecture session. Okay, so it's still in this session also I have included because we have to take the references of the earlier sessions also. Okay, so because of taking that references of the earlier sessions, so I have again included that state preparation and data encoding mechanism and feature mapping and kernel, but we have discussed it in already the details in the last lecture, so we'll be just skipping. But these are some requisite things to understand with the parameterized or variational quantum circuit. Okay, as I told you that ZZ feature map we discussed last class, do you remember? Anyone, if you may respond? Anyone? How many participants are now? 117 right now. So anyone, if you may respond? Do you remember the context of a ZG feature map we discussed in the last class or in the last session?
Yes, sir. Can you once again explain, sir, that one?
Okay.
Hello?
Yeah. Yes. Yes. Hello, madam.
Sir,
ZG. That is.
busy feature, you explained on that day, but it was in a hurry-burry, so we couldn't make it. Just once again, you please explain it, sir.
Yes, yes, yes. So in the context relevant to our that is a parameterized quantum circuit, I'll let you know. Okay, so that is why we have put it on the that is point number 4. Followed to
Yes, sir.
that one, we will just look for some, that is how the support vector classifier would now be here transformed into a quantum support vector. So some methodology we'll be discussing upon some quantum circuit preparation. Followed to that one, we will look over the quantum programming framework, because still we people are going to realize some hands-on experience. So for that one, we need some details about the quantum that is coding. So I'll try
Sir,
to take up.
may I ask you one thing, sir? Sir, in this session, will you explain the coding part also?
Yes, yes, I am going to
Sir, can
explain
you
that.
explain it in detail, sir, step by step, please?
Yes, yes, these are the steps. I'll let you know. No, no problem. Because earlier in the throughout sessions, we do not have any practical sessions now.
Yesterday it was there, sir. He explained the code, means just the code was explained, but not in a detail. So,
Okay,
request from myself, sir.
what code was discussed?
So yesterday, means quantum machine learning is what should be the data pre-processing, encoding, all those things, how to do.
Okay, okay.
But a little bit difficult to understand yesterday's session.
It's okay. No, no problem. So we'll just take care of that one. So now this is still a reference slide. We have already had a discussion related to the quantum machine learning that we started in the last session. Okay, and we know that why we people are looking for a quantum computing, why we people are having such a viewpoint to integrate the machine learning or to integrate the quantum computational aspects to solve the machine learning problem. Okay, so this we people are already known, because we need to devote our time for our hands-on experience. So that is why I am just going to skip. But if you remember one point I discussed, that is it's all about the parallelism. Yes, so if we take care of the parallelism, so we know that in a classical machine we usually implement the parallelism intentionally. Okay, so maybe at the lowest level of processing or at the highest level of processing, we are only including the parallelism intentionally. Okay, so but here this is a kind of a machine that is giving us the flexibility to realize the parallelism by own. So but there were two target areas, if you remember. Okay, there were two target areas I told you. Okay, just wait for a while. These were four different possibilities if we were talking about like CC, CQ, QC and QQ. Yes, so these were our two target areas to work on. Okay, like a classical data that is to be processed using a quantum machine, and this is our ultimate target, to process the quantum data onto the quantum machine itself. Okay, so we are always looking for what the hybrid realization of the system, because as we people are in the early stages of development, everything to be just considered in the same form. So as in the consideration of the hybrid system, because right now so we are here already, because most of the data what we are available with, that must be classical, and we have to transform our data into the quantum compatible format. So under a hybrid system, or whatever the machine learning problem you are dealing with, whether it belongs to a classification problem, regression problem or clustering problem, but we have to take care of processing with the data. So basically the classical computer is taking the care of such tasks like the pre-processing and the post-processing of the learning algorithms. Okay, but ultimately the task would be handled by what? That is a quantum machine, and that quantum machine will take care of what? To prepare the states. Like a quantum state preparations will be done by a quantum machine itself, because it has to now convert the data from the classical format into the quantum compatible format. Followed by that one, some processing aspects would get happened, and some measurement results will come in output. So in a same manner, if you see on the right hand side diagram, we are just looking for any of the model, whatever the machine learning model is available to us in a quantum version or either in a classical version. So they must be that is categorized under a supervised and unsupervised learning models. Okay, so based on our data we have some supervised learning technique, based on our data we have unsupervised learning techniques. Okay, so because the data we are looking for, if we have the features, so there would be an input feature and an output label feature also. So we will be just looking for unsupervised learning methods. Otherwise, if we want to understand the patterns from the data itself where there are no label features output available to us, so for that purpose only, so we have only an option to go for unsupervised learning methods. But whatever the classical data, and based on that classical data we have certain what? The possibilities. So similarly, based on the quantum data, we are here to have certain possibilities, that how to encode the data, how to process the data, how to feature, how to just format onto the feature map, and how to process that particular data. Okay, so for that all purpose we need some revisiting related to the that is quantum machine learning. We have already discussed everything in the detail in the last class. Right now, so we do not have too much time to just explore it. So but let it be with this fact. Here you try to know that we people have already learned that this must be the pipeline, this must be the pipeline, we have to just take care of it. That is a classical data to be encoded, further apply with the machine learning in order to train the model, and then we have to measure the answer, because at the last the measurement of the output or the measurement outcomes would always remain available in the form of classical things. Okay, and based on that one only we will be just going for predicting our outputs. Okay, so because we people have already discussed it in the last class, and we know that the Qiskit is one of the programming framework. It is not only the supported programming framework to realize the quantum machine learning, okay, but it is one of the programming framework you people may deal with, okay, so in order to realize your quantum machine learning programs. So right now, here in the same context, that is based on a quantum machine learning context itself, because now supervised unsupervised learning methods we have, and several, as in like in the previous diagram also, by considering the hybrid quantum machine learning model, several that is algorithms have already been developed, but there exist certain algorithms format which are available in quantum machine methods only, okay, that is usually called as a variational or a parameterized quantum circuits, okay. So now, based on that one, again these things have been classified in terms of either a dimensionality reduction algorithms or the clustering algorithms that have been now clubbed into the unsupervised learning methods, or do we have any supervised learning mechanisms like in the form of support vector machine, neural networks, decision trees, regressors, etc. Okay, but this is as per one of the literature review framework, and they people have already classified that what to go for. Again, that is related to the introduction to quantum machine learning. Followed to that one, we have to look forward for entire background, because only the classical machine learning viewpoint we people are taking, but entire thing will be depending upon what, that is the quantum computational parts. Okay, so the quantum computing related concepts you people have already learned with the qubits, quantum gates, measurement, entanglements, quantum algorithms also like Deuce algorithm, Grover's algorithm, and HHL. I told you that is Horo, Hasidim, and Lloyd's algorithm. That is to solve the matrix inversion problem. Okay, that is to solve the system of linear equations. Okay, so it is one of, again, the famous algorithm. So if you know these all elements, okay, then there is no such problem to proceed with the quantum machine learning aspects. Okay, so this background should be ready first. After that one, we may proceed toward what, that in under the this section, like this section is available in the paper, but the context is that that once you are ready with this background or the fundamental things, then you only proceed for their machine learning model preparations. Either you are going to develop support vectors, neural networks, KNN algorithm, you are performing k-means for clustering, or you are performing some dimensionality reduction task. Whatever the task we are going for, that has to be done specifically if we people are known full with the background details. Okay, like if you people remember my that is the last lecture, I told you there exist certain design strategies. Yes or no? Yes.
Yes, sir.
Okay, so based on the design strategies, we actually know that how a particular algorithm be developed. So these are basically these fundamentals or the backgrounds are just letting us know comfortable about developing any classical equivalent quantum machine learning model. And I told you there are two ways. That is, the first way is what, either to transform your classical model into the quantum model. Okay, that is equivalent model. Otherwise, we can have a dedicated quantum version of the model in order to perform the same task that is to be done by the classical machine learning algorithms. Okay, but but these algorithms are basically developed based on certain applications. So we are known already that what are the suitable applications. So I'm not going to explore, it will waste our time, because most of the time I will have to here, that is, focus on the stepwise hands-on coding experience. So I'll try all of you also comfortable to just go ahead with realizing the codes for quantum machine learning. It's okay. So now, but we have these challenges we people already discussed in the last class, like the challenges in the algorithmic design, followed by the hardware limitation we already known, and the data sets, because the entire data sets or whatever the bulky data set, large volume of data set we people are having. Okay, but the same data set may not be realized directly onto the quantum model, okay, because very limited limitations are coming into the picture for us. And still the encoding, that efficient encoding method is already one of the open research problem to our that is cases, okay. And how our quantum states are really be mapped in order to just realize our answers or realize our predictions, okay. And the quantum noise and decoherence, these are basically very fundamental problem that always deals with any quantum machine. So respective to these things, already we had a discussion in the last class. This is all about the revisiting of our fundamentals, the things what you have learned throughout this FDP program. So these state preparations we are known. This is still the pipeline, because we people have discussed in detail in the last lecture. So this pipeline have to follow. This is as per the quantum machine learning processing, okay. We have to encode the data, apply the algorithm, measure the output. Once the outputs are available, these must be available in the form of classical output. And we know these are the three, like basis encoding, amplitude encoding, angle encoding. These are the three basic encoding mechanisms, okay. I am repeating this word. These three are the basic fundamental encoding mechanism to transform your classical data into the quantum compatible format, okay. But these three includes basis encoding, like the data to be encoded on certain basis, followed by that one amplitude encoding, means the data we have to encode in the vector of that is the qubit itself, or otherwise through the using the angular encoding mechanism, the data to be encoded again. And we know based on the angle encoding mechanism, we have certain structures, like we may apply the angle encoding based on Rx gate, Ry gate, Rz gate. But be assured that applying Rz gate needs always to apply what initially the Hadamard gate, because the Z, that is the Z operation, would not have any impact on what, that is zero initialized quantum state. And we know that what are the complexities. These complexities are actually important, that if you check for the basis encoding mechanism, angle encoding, or ZG feature map encoding mechanism, all require n number of, that is the same number of qubits as you have your data points. But the thing is that when you are referring to the amplitude encoding mechanism, it requires only the log n time. And these all about our feature mapping. Already we discussed that the feature mapping, we are here looking forward for encoding our classical data onto the Hilbert space. So everything, the talk is all about what, that how we are just encoding data onto the feature map. So here coming into the picture, that what do we understand with the feature map here, that is the quantum circuit that is taken with the encoded input data, okay. So once we are ready with the encoded input data and that data is loaded onto the quantum circuit, means your circuit is ready to be processed, okay. Like I already given you the example of Grover's algorithm, okay. So under a Grover's algorithm, our data should always remain onto the circuit, algorithm always remain onto the circuit. The algorithm automatically takes the data from the qubit wire and it processes and generates the output as per the defined measurement, okay. We have to measure our answer, whatever we are looking for, as in the form of desirables. And this is the way that how do we code for the ZG feature map, that it is one of what the feature provided by the Qiskit programming framework. So we have to understand this context again, that this is the first Z operation where this that is what do we call it as to be, this is the first Z operation where we have to apply on each of the qubit, followed by the another Z operations like this. These has to be applied always within the enclosed pair of what, the C0 gates, and that is to be taken care, that would be taken care by the programming framework, okay. We need not to take care upon that how the data will get encoded. We have to just take care that how the ZG feature map is getting created, okay. So once the ZG feature map is ready, means our data is ready for the purpose of processing. Now you come forward for the picture, because this is our discussion, because at least we need 45 minutes or 50 minutes of time for the hands-on realization. So just in a connection to our previous discussion, I'm looking for the variational or a parameterized quantum circuit, and these circuits are basically taken specifically here in a quantum, that uses some rotational function gates. Okay, so some rotation function gates these circuits will be using with some random initialization. Okay, and basically these circuits are used to perform any of the optimization, classification, or any of the approximation related problems. But why these variational quantum circuits are actually that is important here? Because such a circuits or such a algorithm be directly transformed into the corresponding quantum circuits. Okay, so once you are ready with your algorithm, like a variational quantum algorithm, or you will call it like that, variational quantum circuits are ready for your side. Okay, so you may start processing that one. That what is, but how, or what is the structure of this variational quantum circuit you see here? That is as per the pipeline. Again, you look at here, that is as per this flow chart. We usually look forward for the data preparation. We prepare our states. Okay, now after that one, we initialize our quantum model. So initialize quantum model means we are looking for what? Some random initializations. Okay, so some random initializations would be there in the form of some rotational functions. So some rotational function gates are used actually for performing some initialization of the model. After that one, based on the quantum encoded data itself, we use to train the model. Okay, so once the model is getting trained, based on the quantum encoded data itself, we have to finally stop the quantum system behavior and to check for the measurement and read out results. Okay, and we check whether our model is converging with the predictions or not. So once the model is just looking like as per our prediction, so we will stop with our process. Otherwise, this, if you see, this is just a kind of a loop. Again, we have to update some parameters, and based on some parameters updations here, and it would be based on our objective functions. Okay, that we will be just updating, or we keep training our model again. We have to again check for what the measurement outcomes, whether it is converging to as per our expectation or not. That we have to ensure. So for that particular thing, we have the three steps, like the pre-processing and post-processing. I told you in the previous class, that is sections, like the pre-processing and post-processing, these are the two tasks. Okay, like this one, like pre-processing and post-processing, these are the two tasks. Okay, that has to be taken care by what? The classical machine. Okay, so because of these two tasks has to be taken care by the classical machine. So but this is all about what? Our processing of the parameterized quantum circuit, means the quantum algorithm will take care of processing that your machine learning model in the form of the quantum circuit. So whatever the initial data you will be having, okay, so that data would be set to with certain probability distributions. Or hello, hello, anyone has unmuted the mic? Just please keep it on mute mode. It's okay. No,
They
no
are all
problem.
unmuted, sir.
Okay, no problem. No problem. Some
They are
noise
unmuted.
is coming. It's okay. No problem. So whatever the data set we have, we will just look forward for with their probability distribution. Okay, follow to that one, the data would be now encoded and mapped to the quantum states. So once these quantum states are ready, so means the states or the quantum model is available in some initialized random permutation, and follow to that one a variational quantum and the pre-processing scheme that is actually taking this phi of x, that is our encoded vector here, that is to be taken as one of the input. Okay, for our that is unitary circuit, and we know that is what is the context of the unitaries here in a quantum. Okay, every quantum operator to be considered as a unitary matrices. Okay, and we assume that whatever the unitaries we transformations we have, we must be having their corresponding reverse transformations. Okay, such that it should ensure the property of the quantum mechanics, like unitary gets multiplied with unitary dagger. Dagger means what? That the complex conjugate transpose of the same unitary matrix, that should always result to what?
Identity.
Yes, identity matrix. So we have to take care of that one. So a variational quantum circuit that is based on some parameter values of some theta values. Okay, that would be acting here onto this encoder circuit, and it would take some additional that is quantum registers, and these registers are here termed as some ancillary registers, or you may call them as some workspace registers. We have to take care. Okay, so based on this flow itself, based on this flow, whatever the initial permutation we people are having, we will be just looking at with the certain that is outputs, after just performing some measurement task, whether our outcomes are coming as per our expectations or not. If it is not, so we will have to just keep updating the entire circuit. So this is just one kind of the flow that we have to take care, that how a parameterized circuit or the variational quantum circuit be just executed onto the quantum machine. So here we are now proceeding with the task of how the support vector or the quantum support vectors are actually transformed as in the form of support vector. So we know that it is just suitable for performing a classification task, as well as sometimes it may be used for some that is your regressor task also. But the thing is that the support vectors is all about to find some hyperplanes, that is to separate the data points of the different classes, that should maximize some margins. Okay, so and it happens when your data does not remain linearly separable. Okay, so if the data does not remain linearly separable in a lower dimensional space, that by using some kernel transformations, we actually transform what that lower dimensional data onto the higher dimension, such that the data would remain linearly separable there. So the thing is that to support the same concept, of the support vector machine here, the quantum, or in the same analogy, the quantum support vector machines have been developed. But still, some block diagram representations, if you see here on the top, that would remain that block diagram is showing you the overall process here, but in actual, that support vector would just work like in this form of the circuit. Okay, everything is controlled operations here. So now if we see that the support vector is also using ZZ feature map, if it is using ZZ feature map, it still means it is like a parameterized quantum circuit. Okay, that we know that initially we are starting with some random permutation, and we keep on updating the parameters based on our expectation or the objective functions. Okay, now but we have to realize, if we are going to realize these, what quantum we are going to realize these, suppose quantum support vector machine learning model, so we have to use what the quantum machine learning as one of the installed package through the Qiskit framework itself. I told you in the earlier slide, also in the last class, if you remember this one, I told you that the Qiskit programming framework are already giving you the privilege to realize the Qiskit machine learning task. Okay, so based on the same reference, we people are here moving ahead, that if a quantum support vector method is going on, so input data we taken here, feature mappings would be performed. Okay, so the quantum feature mapping is ready. Now the kernel computations will be happened here, and we know after performing that kernel computations, some training of the parameters based on some optimizing parameters process will be going on, and follow to that one, there would be some measurement and for the classification purpose, and we will be reading out our output. So the same things are happening here, because this problem is related to somehow for some matrix inversion problem. Okay, so here in the context of the quantum domain, so if we are looking for the matrix inversion problem, I told you one of the dedicated that is subroutine that is to be used for the design of this algorithm. I told you, if you remember, several design strategies I discussed in the last class, like quantum Fourier transform, if you remember. Yes, yes, anyone?
Yes, sir.
Okay,
Yes,
if you
sir.
If you know the quantum Fourier transform, so inverse quantum Fourier transform is also significant. Yes or no? So like
Yes.
okay, and based on both, we know there exists some other design strategy like to be called as quantum phase estimation, and the extension of the quantum phase estimation to be taken here to solve the matrix inversion problem, that is to solve the system of linear equations. Okay, and that is to be called as what? HHL algorithm. So that HHL algorithm will be completely working on this matrix inversions, okay, like domain, and followed by we have our training data oracle that will take care, okay, of just training our that is data itself, and followed by this is just a parameterized quantum circuit. We have to just run it out and just check out with a readout, some looking for some measurement outputs, whether it is coming as per the expectation like this one. This is the entire process that we have to just form from the initialization of the model, going for training the model, followed by what? The measurement and readouts, and we keep updating our parameters as the form of the parameterized quantum circuits. Now coming down to our that is the significant part again, that still that programming framework is important because it's all about realizing the program. So if it is about to realize the program, so we have to take care that how and why only the cascade programming framework is becoming more popular. Okay, but I do not say I am not like a promoter to the IBM platform, but because these IBM people are giving us a free access, okay, free access to a dedicated quantum machine itself. So because of the people have given us the free access to a dedicated quantum machine, we people are usually referring their IBM quantum platform. Okay, so and we know it that this is open source popular programming framework developed by IBM, and it is and that is it is being realized. Okay, your quantum programs are realized for several quantum applications. Okay, and we have a direct access to the quantum machine, and this IBM people are also giving us support to simulate our program locally on a machine. Okay, so and we know that if we deal with cascade programming, so if we are dealing with the cascade programming, it's a Python based library that people have developed. Okay, so the framework that people have developed, it is completely based on Python, so it is completely familiar to us also. But remember, once we are going to realize our task locally on our machine, so that would need some simulators. So the one of the high performance simulator is known for here, that is known as what? Air simulator. So just keep keep this in your mind, that how air simulator will be used for realizing our task. Now follow to that one, we have some quantum hardware or quantum machines also that that can be accessed to run our program, and it is having some built-in support for the Rovers and Shaw's algorithm. So this is just a significance of a cascade framework, but this is the important thing, that how the framework works at the back end. Okay, so this is as per the IBM publication itself. Okay, so again the things are same, like we have to come up with the problem. If you remember my ladder approach I discussed in the last class, do you remember? Anyone can let me know if you remember the ladders? That is the quantum solvable ladder approach to solve the machine learning problems in a quantum way. Anyone? It's okay, no problem. But in a ladder also, this framework what they people have proposed, like the IBM people have proposed, it is this ladder as per the ladder approach. This framework is already proposed. So whatever the problem we have to come up with the algorithmic solution. Yes or no? So whatever the algorithm solutions we are having in a quantum, so these solutions are basically for our understanding purpose, but the machine does not understand. Yes or no? Machine does not understand the quantum algorithm. Clear?
Yes.
Okay. So, but what the machine understands? Machine understands the quantum circuit. So whatever the quantum algorithm we have to transform that quantum circuit into, quantum algorithm into its equivalent quantum circuit. So the problem, for any specific problem, we have to come up with the quantum algorithmic solution. So once the quantum algorithmic solution is there, we have to transform it to the quantum circuit, and these circuits must be comprising of several gates. We have certain timings, relays, control flows, classical, some parameters, several things are there as per the framework. Because we do not have enough time, but this is significant to understand the framework, that what is actually happening at the back end. Okay, because understanding the architecture is really important once we are going to code for any of the machine, to any machine. Okay, so whatever the problem we have to map the solution in the form of quantum circuits. Follow to that one, at the lowest level of hierarchy, some their corresponding DEX will be prepared intrinsically by the framework itself. Now some transpilation task will be performed. Okay, that includes the compilation of your, that is quantum circuits, and to perform certain optimization measures to execute your circuit at the dedicated backend. So dedicated backend may be the possibility of the real machine, or there may be a possibility of your local machine. Okay, like in a local machine we are going to execute a task under a simulation aspects. Okay, after that one we will be just looking for what, executing of a task. For that one we need certain primitives. Okay, that includes what, some samplers, estimators. So samplers will take care of just realizing their corresponding probability distributions. So whatever the complex quantum states are retained under the quantum state of the system, their corresponding distribution be taken care by their samplers. Okay, followed and in an accordance with the same, the estimator will take with estimator will take the estimator will take what, that is the care of the obtaining the corresponding expected value of our desired answers. Okay, so this is still one of the chain, that is to map from the quantum circuit, go for transpilation task, then go to realize, or to go to execute your task either on simulator or to go for the quantum machine. Followed by, once you are done with your execution, we have to stop our quantum system and measure our answer. So once we are looking for measuring our answer, that is would be called as what, post processing. So that post processing task would be completed here based on some distributions, and we have to check for our observables, that what the measured answers we people are getting. Okay, and that will be mapped with a solution strategy. So this is just a, like again, the pipeline that happens or that gets executed at the back end. Okay, so this is that is the next statement is about the concluding remark, but there is no such conclusion right now, because it was my target to complete at least in 40 minutes of time, because we have to devote the time for the practical realization of the quantum that is codes. So are you now ready to work for the quantum codes? Are you all people ready?
Yes, sir.
Yes, sir.
Okay, so
Yes, sir.
I need certain input from your side. Okay, so first of the things, just please respond, because it's my request, because I need your response. Based on that one only we will be proceeding. uh, have you ever installed any, that is Qiskit framework in your machine, uh, that is during this course of execution?
No, sir.
Yes, sir.
No, sir.
No, sir.
No, sir.
Somebody
No, sir.
are saying yes, but it's okay.
No, sir.
No, no, no.
No, sir.
No,
No,
sir.
sir.
No, so it's okay, no problem. So first of all, you try to understand. Okay, it's okay, no problem, no problem. And we'll see. We'll see. Just let me take first empty slide. Okay, one empty slide I need. Just wait for you first try to understand what is requisite here. Okay, that is to work on. So the first thing is, there are many ways through which you can execute your quantum codes on different platforms. Okay, the first possibility to execute your quantum code on your platform, that is to be called as quantum, we usually called as quantum simulation. Okay, so for simulation task means the classical machine will be installing some Qiskit oriented framework. Okay, and that framework will support what, some quantum environment under the classical machine to realize a task. Clear? So that quantum simulation is first of all possible. So that possibility of the quantum simulation is there, either to run on locally on machine, what I am calling locally on our machine. So under our machine, we people are just executing our task. This is the first way. Another way is there, the same quantum simulation you people may realize. So the same quantum simulation you people will be realizing over your local host machine. What I am talking about? Local host machine. Yes or no? Are you getting these things? First, I am talking about the locally at the machine. Okay. Standalone, I am just executing my task. Now I am taking care of executing the same simulation local on the local host. Okay. Otherwise, we can also perform the simulation on the cloud platform. Okay. On the cloud platform. So like on the cloud platform, you may use a Google Colab also, because the Google Colab is giving us a Python based environment. Yes or no?
Yes, sir.
And the
Yes, sir.
Python, and we know that Qiskit is what?
Yes, sir.
What is Qiskit? Qiskit
One.
is, it's a Python oriented framework. Clear?
Yes.
So it is compatible here. It is compatible here that if you have the simulation using a Qiskit programming framework, so either you may run them from at your local machine, you may execute them on local host configuration, like using your Jupyter notebook. Okay, or like let me write it down, like Jupyter notebook. Okay, note book I am writing, and locally on machine, so you may use your any of that is like Anaconda framework you may need to just realize your Python environment and just to execute the task, like some Python environment should be there first. Okay, now the second is the way to realize your, that is quantum realization, that is a realization of your Qiskit codes on a quantum machine. Okay, so I'm talking about the machine, that how a quantum codes would be executed on a quantum platform. So for that one, we have the free subscription plan. Okay, that is a free plan we people are having, that is based on what? IBM. Okay, so on IBM platform itself, we have a free plan to execute our quantum circuit. Understood? Okay, so we have several ways through which we people may execute the task. Understood? So now you first let me know that what may be now suitable to you, because we are still looking for suitability option. Because if you configure your machine, if you need the steps, so I will let you know right now.
Working with local host.
Working with local host machine, or you are just executing it on your, that is machine
Locally. Execute it locally.
So okay, any so if you want to execute the task locally on your machine, okay, so there exists certain steps you just please follow. There is very important steps, there are very simple steps to be done. Okay, but I cannot let you know with these all steps, because we do not have time as per our that is committed lecture. But I am just letting you know that step-wise process. That is the first thing what you do to set up your program locally on a machine. You first install any editor. Okay, like in a code Python code editor. So I am just giving you that you install, suppose Visual Studio Code. Okay, so directly go to Google, okay, write down Visual Studio Code download, like here. It's visible now. My window is visible.
Yes, sir. Yes, sir.
So when you go for download Visual Studio Go, you that is code, you will find the that is first link. That is the topmost link. As per your machine configuration, you just download your Visual Studio Code. Yes or no? Is it fine? Is it fine?
Okay, sir.
Yes, sir. Yes, sir.
So first of all, so you do one thing, that download the Visual Studio Code, and followed by you have to install. Clear? Install that Visual Studio Code in your machine. Now the editor is ready, okay, but we need some Python environment under our machine. Okay, so within our machine we need some Python environment. So you have two options. So either you can go for Python download directly from the python.org, that is Python website. You go to the Python website and you install the latest version of the Python. Otherwise, you have the possibility to download and install Anaconda also. It is also providing you the Python framework. Yes or no?
Yes.
Okay, so I am writing in or. Either you go for Python or you go for Anaconda framework. Okay, so framework I would suggest always, because certain dependencies, okay, that would be taken care by the framework itself. So sometimes it remains easier to go for realizing your codes under this environment. So again, whatever you are doing, okay, you first go for their downloads, and followed by what? That is, go for installation. So for the same also, there is nothing to be worried upon, that here you write down Anaconda download. Okay, so you will be having again the first link again. So under that link, you just look at for this skipping of registration. You skip this registration, you will find some that is the distributions of the Anaconda. So as per your that is a requirement of the backend machine, you just go for installing your Python version. Okay, like for Windows, if you are looking for, or for any machine, so you just specifically go for. Is it fine? Is it fine? These two steps fine?
Yes, sir.
Okay, now I'm letting you know the third step, then what to go. First, install the, that is download, install Visual Studio Code, followed by download and install the Anaconda or the Python. Followed by that one, you go for install extensions. Okay, extensions at VS Code. So at VS Code, Visual Studio Code itself, you go for installing certain extensions, and that extensions should be related to what? Python. And suppose like you also want to run your program on locally on the local host machine. Okay, so like on local host machine through Jupyter Notebook, if suppose you want to learn sorry, if you want to run your program. So for Jupyter Notebook I am writing. Okay, so these Python and Jupyter Notebook extensions, you first go to the Visual Studio Code and install them. Understood? So this is the third process. So for this third process, you do nothing. If suppose, let me start with first of any one of the code. No worries. First you see this will show you the extension. When you click it on, okay, so these are some extensions, and you have to check whether here you write down, suppose like Python extensions. Okay, so Python environment should be enabled like this. Like Python environment is already ready in my machine. Okay, so it is just showing me the button of uninstall because it's already installed. Clear my point? Clear my point? So for you people, if you are that is freshly installed with that software, so it will give you the install button. Okay, So once you click on install, that extension would be automatically installed. Is it fine? Is it fine?
Okay, sir.
Yes, sir.
Now, followed by you type Jupyter and you check for what? Jupyter notebook installation. Still it is showing uninstalled for my machine. But remember, if you have freshly installed, okay, so this will give you the install option. You just click on the install option and just realize your code. It's okay. So once these three things are ready in your machine, then you go for the fourth one. Okay. Now, the fourth one is you have to install the Qiskit framework. Okay. Like I am writing for installation of quantum framework. Quantum. Actually, I am really in a hurry to write because writing, I did not think to just let you know these things for the sessions, but it's okay, no problem. Installation of quantum programs. Sorry, installation of quantum programming. It's a programming framework I am writing. Framework. So for the installation of the quantum framework, first you write down the command. What you need to do, you open. If suppose you have opened the, that is command prompt, you open. Otherwise, if suppose you have installed the Anaconda, okay, so you open the Anaconda prompt. Okay, Anaconda prompt. Actually, just because of hurry, I am not satisfied with my writing right now, but it's okay, no problem. So the context is clear now, that what we need to do. Yes.
Yes,
The
sir. But
people
can't we go with the cloud platform directly, sir?
yes, the cloud platform. I told you this is another way. That is to go for directly the collab. Okay.
Okay, okay.
So I'll let you know through the cloud platform. No worries. Okay.
Okay.
Wait for a while. Okay. My system is also ready, but no problem. I'll demonstrate. Okay. Now, so open the Anaconda prompt. I am just letting you know that the possible steps, because the few people have asked that how to set up a local machine to run the quantum programs. Clear? So now the Anaconda prompt, under the Anaconda prompt, we have to write down the commands like pip. Okay. Install. First, you install what? Qiskit. Okay. So Qiskit is a programming framework that is containing all the requisite APIs. Okay. And the libraries, they would automatically be installed if you see your machine. Okay. So your machine will be installed with the latest Qiskit framework package. Okay. Now, followed after that one, these are some requisite things to be installed. What I am letting you know. After that one, you also see for what? PIP install Qiskit. Okay. Within the array bracket, you write down visualization. Okay. So it is all for the visualization of our that is the task, because the model we are going to deal with, it is what? It's a probabilistic model. Everything will be visualizing in the form of, suppose, the probabilistic histograms. Like sometimes there will be some graphical vectors we'll be dealing. Sometimes there would be a circuits. Okay. For that one, you install the visualization. Followed by that one, you install the backend simulator. What simulator name I told you? If you remember, what? Air simulator. This is high performance simulator backend, that is giving us the backend. So PIP install, but you remember that how to write. That is Qiskit hyphen you use. Okay. AER. So Qiskit Air would be your would install your air simulator. This air simulator would be installed if you just run that command. Okay. And specifically for running your machine learning task, okay, you have to install what? PIP install Qiskit hyphen machine hyphen learning. Okay, and all things, all letters must be in a lowercase. Clear? These things fine?
Clear, sir.
Okay, so these
Yes,
are
sir.
some necessary steps you people have to just complete at your backend to just set up your that is quantum environment under your machine. Okay, so first of all, because do you have the realization related to the basics of the quantum? But still we have half hour of time, no worries. No.
No, sir.
So let's start with the basics, because still we have to take care of realizing our quantum, that is the code related to the encoding mechanism and the code relating to our that is feature mapping, that is to realize our parameterized circuits. Okay, so here let this extension be over. Now you see, or this is the environment where I can execute my code. Understood? This is the first thing you try to understand, that by turning out my own space, okay, it will ask to select for my kernel. Okay, so I'm choosing here my base kernel to execute this task. Okay, first you just only look at the interface, that how it is happening, then I'll let you know through the Google platform, no problem. Okay, just wait for a while, let it execute. Just wait, it would take time, machine is taking time. Okay, let me clear with the output. Now this actually a code that would realize a superposition. You know the what the superposition? Yes, what is the superposition? If suppose we have a qubit that is initialized with 0 quantum state, okay, on that qubit when we apply the Hadamard, it transforms what? Your qubit into what? Cat 0 plus cat 1 by root 2. Yes, and that is equivalent to what?
Yes.
The cat plus state. Yes. Okay, now you see,
Yes.
we want to execute this code here through the Qiskit program. So this is the very basic program I am letting you know first, because it is again one of the requisite, because I'll have to let you know that how the code actually be executed. Okay, then only we can discuss about the encoding mechanism and feature mapping part related to the quantum machine learning. So now here you see, let me do one thing. Let me divide this part. Is this fine now? What we are, just wait. Is this fine? Yes,
Yes, sir.
these
Yes,
steps
sir.
are fine, no problem. So because to set up your machine like locally set up, so I have already told you. Only one thing I am letting you know. Once you install this extension, like this Jupyter extension, okay. So once you install this Jupyter Notebook extension at your Visual Studio Code, you may open your Anaconda prompt and you may write down Jupyter Notebook. Okay. So once you write down Jupyter Notebook, your Jupyter Notebook would be opened locally on your host machine. Okay. Okay.
Okay, sir.
Okay, sir. Okay.
So otherwise you first see. Let me know you here. The fonts are visible.
Yes, sir.
Okay. Now you see, this is the Visual Studio Code, the editor I am using. This is as per this first. Okay. Locally on machine. So locally on machine, how I am going to execute the program? Look, initially it's our responsibility to import some libraries. Okay. We have already installed the Qiskit package. So now from the Qiskit package, it is as per the importing of package, we people are taking the convention. Now from the Qiskit package itself, okay, we are initially importing some quantum circuit. So this basically, this quantum circuit is a class here. Understood? Understood?
Understood, sir.
Okay. So this quantum circuit is a class, And this transpile, if you remember the framework, do you remember the framework?
Yes, sir.
Yes.
Yes.
So
Yes,
why
sir.
this transpile is required? I told you it performs some that is what compilation tasks
Yes.
followed by optimization tasks
Optimization is done.
to execute the optimized quantum circuit at the dedicated backend. Okay, whether the backend may be the simulator, backend may be the real quantum machine. Understood?
In
Understood.
fact, sir, it might be a combination of transformation plus compile.
Yes, that is the transpilation task. Okay, so now these two things are clear that why we are importing.
Clear, sir.
Now, followed to that one, you see from the Qiskit Air. Have we installed the Qiskit Air? You see, I told you. Yes.
Yes, sir. Yes, sir. Yes, sir.
So Qiskit Air would provide what? It would provide what? The high
Simulation
performance simulator.
environment.
Simulator, sir.
Okay, it's a simulator, and the name of that simulator is what? Air simulator.
Air simulator.
Air simulator.
So this air simulator we are importing from the Qiskit Air. But remember the convention. Okay. While installing that package, I was using hyphen. You see. Yes.
Yes, sir.
Yes, sir.
While importing, I am using what? Underscore.
Underscore.
Now
Okay.
in
So
underscore.
because the standardization of this language has not been done. Okay. So you please we have to that is compromise with these specs. Okay. So it is air simulator we people are importing. Now from the Qiskit visualization package, because visualization we people have installed. Yes. So we'll take the facility of plotting the histogram,
Plotting the
and because the
histograms.
histograms are needed at all to just plot the probabilistic outcome that comes after the measurement. Clear my point?
Clear, sir.
Okay, sir.
And the matplotlib we people are just applying just to print our quantum circuits or some that is graphical outputs. Okay. Now these are some basic importing of libraries you remember. Clear my point? Okay. Now after that one, what to take care? This is a single line of code that we need to create a quantum circuit. So this quantum circuit is a class. Okay. I have already discussed. We have imported this class or not?
Imported, sir. Imported.
Here if you see, this quantum circuit is basically a constructor. Okay. So it's a default, it's a parameterized constructor here, and that is taking two arguments. Clear? So first argument is showing the number of quantum bits available in a circuit. Understood? And this will show what? The number of classical bits available in a circuit. Is it fine?
Okay, sir.
So there would be a quantum circuit that would be created on 1 qubit, 1 classical bit. And we are assigning that quantum circuit into one of the instance variable. So this QC is basically an instance that is to be called as object of the quantum circuit. Clear?
Clear, sir.
So, sir, it is a 1-bit quantum system.
Okay.
But how this another classical bit is having some significance here?
Sir, classical bit must be there because as we know, once the quantum system is stopped, means once we measure the quantum system, we will get what? The classical outcomes. Yes or no?
Okay, so for measurement it is there.
For measurement only. I demonstrated this thing in the last class. If you remember, just let me write down IBM.
No, I got it, sir. I got it.
No,
I got it.
it's okay. IBM circuit composer. Let me write down. Once you write this IBM circuit composer, you will find the link like this. So if you remember, okay, these are 4 qubits. So based on these 4 qubits, these are the C4 stands for there are 4 classical bits. Understand?
Right, sir. Right, sir.
So based on that one, if you see, these are the quantum states. Okay.
Okay.
At the left hand side, you will find what? Some already prepared quantum gates. This is IBM
Right.
quantum platform. Okay. So now I am deleting. I am clicking left on left clicking. You will find this deleting option. Now I have deleted. Okay. All. So this is what? Only
1 bit.
1 qubit. So for
And
1 qubit, how many
C1.
how many classical bits?
One.
classical bit I need. Okay. So
Right.
here, if you see this assembly language program, it's a quantum register created with one class quantum bit and one classical bit is created using classical register. Okay.
Right, sir. Right, sir.
Now, if you see, I am going to realize the superposition. So this header mart we have to apply. Otherwise, before header mart, what happens? If you see this block vector, it is what? Cat 0.
Cat 0.
Okay. And here you see that cat 0 is available with 100% probability because system is not available in a quantum system. Yes. But
Right.
now, once we are applying this header mart to this one, you see what happens.
Both half and half.
But this
Positive
is
comes.
probability. But these vectors must be there in a realization. Yes or no?
Right, sir.
Once you see, I am looking for this tab and applying for vector. You see, what are the vectors? This is 0.0707. Yes?
Right, sir.
So what does the mean of 0.707? It means 1 by root 2.
Right, sir.
Okay. So what do we understand? That 0 plus 1 by root 2, this is the state. 0 and 1, cat 0, cat 1, both are available. Yes?
With equal probability.
Probabilities, how do we get the probability? We apply the
By
modulus.
amplitude square.
Yes. No, modulus square, sir. Modulus is important because these are the complex amplitudes. Okay.
Yeah,
So
yeah.
the
Modulus.
complex numbers are we people are dealing with. So the for measuring the complex values, the modulus operation in a square format to be applied. Clear?
Right.
So these are like 1 by root 2. Modulus square is giving us 1 by 2. So there is a half chance to measure the answer. So this is the circuit that we are already ready. We may set up the same circuit by clicking on this button and we can run the same circuit on the dedicated hardware. Clear? But that hardware requires the credentials. Okay. Right now, so I can demonstrate everything, but we are limited with the time and still I am awaited with my encoding part. Okay. So just wait and come up here. So the context is we have created this quantum circuit. Like this part of the circuit is ready. Now we want to apply the header mart. Now you see, this is the one line code. Quantum circuit. This is the object. Yes. On that object, we are applying this header mart. It's a method. Okay. So the header mart we are applying on which? This actually shows the index of a qubit. What it shows? The 0 is indicating what? Index. Here if you see, what is the index of a qubit? 0. Okay. So on a quantum platform, it is showing as an array subscript. Okay. But here if you see, this is showing as a parameter of your method. Clear my point?
Right.
Okay. So this header mart is a method that is applied on what? The 0 initialized quantum state. Oh, sorry, 0th index qubit. After that one, what to perform? We have to perform the measurement. So here you will find the measurement directly. This is the operator on Z basis. So if you see, once you perform the measurement, your system would be there in one of the measured state. Clear? One of the random state would be coming like a flipping state of a coin. Okay. So
Right.
now, so how do we measure? From the quantum circuit itself, this is a measure method. And this measure method will take what? The 0th index of qubit, that is to be measured under 0th index of classical bit. Understood?
Right.
This is as per the same circuitry of this quantum circuit. Okay. After that one, this is the preparation we have to take care. Like at the back end, we want to execute our task. So now air simulator we have imported. Yes.
Right.
So based on that air simulator, here you see, based on air simulator, this is a constructor called default constructor we have taken. And based on this default constructor, this simulator is the object. Okay. A reference, an instance is created. Okay. Now, what I told you about the transpile? What was transpile? Transpile
It is compiling and optimizing the
compiling and optimizing the quantum circuit for the backend. Okay, for the target backend. Yes. So now here you see the compilation, that is the transpile, is taking two parameters. First one is what? Quantum circuit.
quantum circuit object.
Means the object that is to be compiled, means the quantum circuit that is to be compiled, optimized
And simulator.
and to run on which backend. This is showing your backend. Understood?
Right.
After that one, from the simulator itself, okay, we are having some static method called as run. So from the simulator object, we will run this method, and this run method will run what? Compiled circuit. So this compiled circuit must be a transpiled circuit. Understood? So each time when the circuit will run through the simulator, their corresponding result will be measured. Okay. Their corresponding result will be now taken back into the result variable. And this result, each time that result will be calculated with their counts. Okay. Like the default number of times we want to execute our code, it would be 1024. Clear my point?
Yes, sir.
Okay. So 1024 is the default number of shots that is to be executed. Clear?
Yeah, so they are something like epochs.
That is epoch. Okay. But epoch means multiple iterations. Okay. For the entire process. This is just a sub part here. Number of shots we are going to run a simple specified circuit here. Okay. So now here you see, here one parameter I missed, that is called as shots. If you write like shots, okay, shots value if you assign, so it would be assigned with certain values. Otherwise, if you skip, so by default the number of shots would be 1024. Clear? After that one, and you remember, it's a parallel machine. It's a hardware that is giving you intrinsic parallelization. Nothing is happening in a loop. Yes. There is such a loop we will be writing like for I equal to 0 to 1023. Okay. And my code will be running at the back end. Okay. Some noise is coming. How I am just getting this noise? Just please. Okay. Now see. So now after that one, what to take? We are printing that count, plotting the circuit. Okay. With this draw method. Okay. Plotting this circuit and plotting the histogram. Now you see, let me run this code. This is a kind of circuit that we have prepared. If you see, have we prepared the same circuit on the composer? Okay, this is out IBM cloud platform. Okay, but the same circuit we have executed on locally on our machine. Now I'm plotting this histogram. You see, let me just reduce. Now you see what happened. Out of 1024 time, 499 times 0 got measured, 525 times 1 got measured. Now I am running the algorithm again. Now you see, the probabilities are changing or not? See, they are changing or not? Yes?
Changing, sir.
But
Changing?
how the sum is coming more than one, sir? It is something like 512 and 512. Okay, it is out of 1024.
It is out of 1024, sir.
Got it.
Okay. If you set it to, suppose like the shots I am going to set here, like shots I am assigning to 1000. Okay. And let me run it again. The code. You see?
Correct.
Clear? So the shots you people may just write it. Okay. Otherwise, if you skip, so by default, the IBM actually runs your circuit for 1024 time. Clear?
Yes, sir.
Now you see that how to go for installation. Now you see here. Just wait. My machine is visible now. Just wait. Is it fine? Visible?
Yes, sir. Visible.
I am writing Google Colab. Now you see. Okay. Let me just open one. You go to Colab and you open a new notebook drive. Like, let me just close these all windows. Okay. So this I am letting you know about what we people have run the program locally on a machine. Yes. The same program you may run through the Jupyter also. Okay. How you will be running that program through the Jupyter, I am just letting you know. One minute of time. You just please see. Here, you go to start, you write down Anaconda. Suppose you have installed with Anaconda. Clear? there would be some prompt coming to a, okay, you write down Jupyter notebook, you press enter. What happened? I think what's just now, let it be, because already running with the time late. Look at here. I think some writing mistake I am doing, but it's okay, no problem. You come here. This is what your but Jupyter notebook you will have to write down. This Anaconda will open your Jupyter notebook file, okay, and sorry, on a local host machine, and you will have to perform the same task without installation. Understand?
Yes, sir.
Without installation, you will have to proceed to execute the same algorithm. That is same code. Let me just reduce it. This code you will have to execute directly. Clear? So now, but because this is a cloud platform, and under a cloud platform, we do not have any privilege that my Qiskit environment is not ready. So we have to we have to make our environment ready for our machine. Okay, so now let me just install. What to write? Qiskit, sorry, pip install Qiskit. Yes,
Yes.
and just run this cell. This is the demonstration I am giving you. Okay, because we are still left with Murthy sir.
Sir,
Sir, I request you to just please inform that is the next expert
okay.
to join because I will be late by 10 minutes only.
No issue, sir. No issue.
So just
You are
please,
most welcome.
just give my apology because I cannot be able to complete it right now. Okay,
No issue. No issue.
is expected. Just wait for a while. So this, can you be able to see this installation? Yes.
Yes,
Yes,
sir.
sir. Yes, sir.
Like if you see the Qiskit 2.1.2 is installed here in this machine. Understood? Clear? After that one, what to do? Qiskit. Sorry, what to do? You just copy here. Okay. Now go for what to install? Like
Visualization.
visualization. Install it. Okay.
And then machine learning.
Okay. Now that visualization is ready. After that one, what to go for?
Machine learning.
No, that is
Test
Qiskit
simulator.
AR.
AR. Right.
Okay. Machine learning is for machine learning tasks.
Got it.
This is the basic setup for realizing your quantum task. Clear?
Okay.
Now the Qiskit AR simulator is installed. Clear? Now the Google Colab is giving you the Python environment. That is the first thing. Okay. Now we people have created our local environment here at the cloud itself. Okay. For our quantum environment. Understood? The quantum environment is ready. Here. Yes.
Yes, sir. Yes, sir.
Now what to do? We have to copy the code. You copy the code. Similarly, the code I will share to Murthy sir. Okay. Because we may or may not be able to just available with the time. Okay. So the code I will be sharing with the Murthy sir. You just please follow the steps what I told you already. Okay. Actually, I have taken that as the burden. Okay. I was
Tick,
not
tick.
there.
Right, sir. Right, sir. Right, sir. Right.
Just please follow the steps and execute the file. Clear my point? Now
Yes.
here, the code is run. Okay. Follow to that one. We need only a single statement. That is what? One qubit and one quantum circuit. That is one qubit and one classical bit. Followed by what? Hadamard we need to apply. We are just copying, pasting. Just running. Okay. So now Hadamard is run already. After that one, what to go for? Go for measuring. So now go for measurement.
Measurement.
This is the measurement. Already instruction sets are ready for our that is target cloud machine. Okay. After that one, we have to take care for what? That back-end preparation. So this is as per the back-end preparation I am taking. Okay. This is for the setup of back-end simulator, and transpilation task would be automatically done there at back-end. Now let me run it. You see, the same circuit is available,
Yes.
but here you see the counts 5075493. Here counts are different. If you run it, you see. Yes.
Yes, sir.
Again, the things are changing. If I run it again, you see, changing. Again, changing. Yes or no?
Correct.
So if you plot like this histogram also, you see what is happening here. The histograms are changing. Based on our running instances, histograms are changing now.
Changing.
Okay, we have to run this histogram also like this. So this is the complete quantum behavior that happens usually. Clear my
In
point?
case, sir, in case if we add one more head mud
Yeah.
after the head mud which is being applied,
Okay.
then we will come back to state 0, cat
Yes,
0.
your previous state. You see here, because this composer is very important for that one. You see, this is
Let
the
us try
header
that. Let us try that also.
Just wait. This is header mod. Okay, header mod is giving you the equiprobable superposition of zeros and ones. Okay, now again applying the header mod. So what was the initial state? It was 0. Yes or no?
Correct.
So now applying header mod again. You see.
Yes.
Clear? So header mod is actually header mod followed by header mod. You will get the previous state. Suppose my previous state is 1. You see, I am applying header mod right now. This is not operation. Okay. So this not operation is specifying that header mod is applied on 1, means it is 0 minus 1 by root 2. Clear?
Right.
So now on which, if I again apply this header mod, then you see what happens.
Right, sir. Right, sir.
Clear?
Becomes
So,
clear.
this is just like a toolbox for you. This is IBM circuit composer. Okay. So you will just drag your operators, play it with, because if you know the fundamentals, if you are ready with the quantum gate circuit, so you may just go for executing all. Clear my point? Okay.
Right, sir.
Now you come down to the that is other aspect again.
And this simulator is also available as open source.
Which one, sir? Just wait.
Sir, the simulator which you are showing
This
is also available as open source.
Yes, I already I only typed the name. You write down IBM Quiskate. Sorry, IBM Circuit Composer. You write down. Okay.
ठीक है, sir.
As
Right,
you
sir.
type, you will get the topmost link like this. Okay.
Got it.
This is the default interface that would come to you. But remember, if you are just preparing your circuit like this, I have prepared this circuit. It doesn't mean that circuit is executed. It is just giving you the visualization aspects, that what is happening under the quantum system. Clear my point?
Right, sir.
If you want to run, you will have to just click on this setup and run button. Once you click on this setup and run button, it will ask you to provide your credentials. Okay.
I see. Okay.
Clear? So you first create your IBM account. Clear? After that one, you just click on that is you apply your credentials, log into the IBM account and run your circuit.
Okay.
Run your circuit. Now come to the machine learning part again, because already, sir, my task got over. Okay. Already the time is over. No problem. But you come down to our aspects, that what we wanted to just realize in our machine learning parts. Now, what we were talking about? What were the basic encoding mechanisms? Basis, amplitude, encoding. Yes or no?
Yes, sir.
And followed by, to realize the parameterized quantum circuit, what do we need? We need what? ZZ feature map. And the feature map be created like this. Yes or no? So like up now, it's the time coming. And now you people are known that how the circuit be interpreted, and you know the way of writing of code. Yes or no?
Right.
Now you please pay your attention. Already we have reached to our time limit, but I requested for 10 more minutes. So just please cooperate with your attention. Look at here. From Qiskit import, quantum circuit you are known. Just please respond. You know why we import the quantum circuit?
Yes.
Transpile mechanism, you know.
Yes, sir.
Air simulator, clear.
Yes, sir.
Right.
Yes,
Plotting of histogram, why it is required from visualization, you know.
Right.
right.
State vector is again actually from Qiskit, because we have installed the Qiskit package. There is a sub package of quantum information. So from that sub package, we are importing state vector. And that state vector is just like this. Just like this. This is a block sphere that would be printed in our code. Okay.
Okay.
So just to simulate that behavior, we have imported this one. And this is from Qiskit circuit library. So the Qiskit, there is a sub package circuit. From circuit, we are using library. And from there, we are importing what? ZG feature map. Now,
Easy feature map.
ZG feature map. It's a Qiskit programming framework supported feature map. Yes, that is used to load your quantum encoded data onto the quantum circuit. Understood?
Yeah. Right.
Now, NumPy is taken for mathematical calculations. Okay. And this matplotlib, so you are known. So I think this context is ready. Okay. Let me run this cell. The same code I will share with Murthy sir. Okay. The code you copy. Okay. And it's your choice now. You may run by setting up your local machine, or you are running it onto using a
Cloud.
Jupyter notebook on your local host machine, or you are running it onto the Google Colab, okay, through the cloud plan. But on Colab, please take care of realizing your that is for setting up your
Environment.
quantum environment. Understood? Now, this first importing of library is successfully executed. Now you come to the basic encoding part. Okay. Now, before to that one, you first be connected with what was the basis encoding. If we have any quantum state like this,
It becomes cat 10, cat
like
10.
cat 10 means it would be cat 10. So how to make it? I have defined one method. Okay. So in a method, this method named as basis encoding. Okay. That is taking binary data as an input. Clear? So that binary data input, their corresponding length we need to calculate. Okay. And we have to assign it as the value of n. And why we are calculating the length of the data?
Because that length is actually required as a qubit
Yes,
system.
because already we discussed in a basis encoding, angle encoding, and ZZ feature map. In all, we require same number of qubits. Yes.
Yes.
The number of, as the same number of data points, we need to take the same number of qubits, irrespective of what amplitude encoding mechanism. Now you see, a quantum circuit is actually prepared. Okay. So this is a
Yes.
call. So quantum circuit, this quantum circuit is actually prepared based on n qubits and n classical bit. Now you know the context.
Got it.
Okay. Followed by, we are just running this loop. Okay. For I, and to be taken in a bit. Okay. And we need to enumerate that bit in a reverse order of the binary data. Because you listen, how do we write? If suppose I ask you to write 3 in binary, how do we write binary in 3 bits? 0 1 1. Yes.
Yes.
So the order I actually used, it is from left to right. Clear or not? But we know where is the LSB? Rightmost part. Yes. And where is the MSB? And the leftmost part. So we usually write our string like in a manner, but we interpret the string from right to left. Yes or no?
Yes, sir.
So for
So I
that,
have one doubt, sir.
yes.
Sorry, sir. So binary data you have given us, sir. Is it an entire data point means you will be having a multiple features? All those things has to be converted to the binary data only?
Everything, because at the lowest level of processing, everything would be binary, madam. Okay. But the thing is that once you are processing it through the quantum machine, it would be converted into the quantum state format.
Okay.
Okay. So that is why here we people are simulating that how the binary values, okay, how the binary values would be now encoded into the form of quantum state circuits, like in a quantum states, and how these quantum states be actually represented onto the quantum circuit.
Okay, sir.
Okay. Just wait for a while, you will get to know. When it comes to picture, means when it comes to realization or the visualization, you will get to know better. Okay. Just see
Okay.
here, if a bit, what I am looking forward, if a entered bit is assigned to 1, means at that time we have to apply what? On the same quantum circuit, we are applying X gate onto the ith index qubit. Clear? And why we are applying X gate? X gate means 0 will become 1, 1 will become 0.
0.
Okay, so that is like an X gate, because the initial permutation of any qubit must be what? It is in a cat 0 state or cat 1 state.
Get 0.
So all qubits we are considering that they are in a cat 0 state. So that is why whenever the binary instance is 1, we apply the X gate. Clear? Followed by that,
Right.
we will measure the circuit in a range of n qubits. Okay, and n classical bit, and followed by that one, we will be returning the instance of that circuit. Clear? So this is just a defined method. Just let me run it. The method is run, but it is still a template. We have not called this function. Now this is, you are known that why do we create for a backend preparation? Yes or no? Simulator instance created. Clear?
Right. Right.
Now you come. This is the realization of task. Basis encoding. So under a basis encoding, this is the method call, basis encoding, and this is the binary string we are passing like 011. Okay. So the 011's length be calculated here as 3. The 3 cross 3 circuit will be created. Okay. And whenever your binary string would be having an instance of 1, the X gate be applied. Yes or no?
Right.
Okay. Now after that one, this basis encoding means the means this instance what is now returning from that defined method QC, that would be assigned to the QC basis. Okay. The reference is actually, these are the references created. Now after that one, the transpilation task is happening here. After the completion of transpilation task and this running task and these all things, you are known, because already I discussed in superposition example. Understood? These all tasks, transpilation, simulator run, and then get count and measurement and plotting of histogram. Yes or no?
Yes, sir.
So let me run it. You see what is happening. This was my data. You see here. The data was what? 011. Clear? So because the data was 011, the circuit is looking like this. 011. So what is here the LSB? I told
1.
you where is the LSB? LSB is the rightmost bit. Yes or no? So
Yes, 1.
Q0, this Q0 is represented here as a least significant bit. Understood? Okay. And this is the MSB. Suppose now let me just change the data. I'm changing the pattern as to be suppose 101. Run it. You see, this is your data that would look like. Yes.
Yes, yes, yes.
So this is the representation of a data in a quantum world. Everything is different. I told you in the that is
Sir, in case if we made all zeros, then all X will be lost.
all X will be lost.
Right.
Okay. I'll share the code to Murthy sir. Okay. And
Please,
you
sir,
run it
please.
accordingly. You run just I have already discussed with the parameters. Now amplitude under the amplitude encoding method, you first try to know that what was happening. The data to be encoded here in the amplitude of the vector itself. Okay. So we have taken suppose like 2 data. Yes, like 3 and 4. Their mod be calculated. And the new data points would be like what? 3 by 5, 4 by 5 in our quantum world. Yes or no?
Yes.
So that we discussed. So now this is the definition of amplitude encoding. Now directly we are taking what? From the NumPy object, we are taking the linear algebraic method, and from what? We are using
norm
what?
method.
The norm to calculate the norm of the amplitude vector. Okay. That norm be assigned here, and the amplitude or the vector to be normalized here, like 3 would become 3 by 5, 4 will become what? 4 by 5. Okay. So for that purpose, the normalized vector normalization be done by dividing it with the norm value, followed by the state vector representations would be there, and the state of the block sphere be returned there. Okay. So this is the simple definition of the code. Now if you see, it's still the same data, because as to map with the theoretical facts here in the practical mapping I have taken here. Clear? Now
3 by 5, 4 by 5 will be the result.
that is 3 and 4 I have taken as a data, because the classical data points were 3 and 4. Okay, it would become 3 by 5, 4 by 5 here in quantum. Clear? Now you see, amplitude encoding is called based on amplitude data. Data is a vector like 3 and 4 we are passing. Clear? After that one, this state amplitude be printed here and the drawing of block sphere will be done. Now you see what happens. This is your vector looking like. Okay,
Right, sir.
this is your, and it is somehow inclined from this x basis.
Towards
Can you-
cat 1. It is now inclined towards cat 1.
That is like the value it is now holding.
4 by 5.
It is what? 3 by 5 and 4 by 5 both are contained there itself with the vector. Like this is
Right.
every vector is associated with the probability amplitude. Yes or no?
Yes, sir.
So probability amplitude is a complex amplitude.
Right.
Yes. So you see what is the value of this amplitude? 0.6.
0.6.
0.6 means 3 by 5.
Yes.
What does the mean of this 0.8? 4 by 5.
4 by 5.
Okay. So these are represented here in a complex amplitude. Clear? So this is just your way of representing the data in amplitude encoding form. Now you come down to angle encoding. Now if you see angle encoding, feature vector to be passed and again the length to be calculated, because we know the same qubits are required. Based on that one, the same length of the quantum circuit and classical classical bits to be created. Again we have to enumerate our feature vector. Based on the enumeration of the feature vector, we will be just applying some angles. Clear? So based on angles, I told you in the theoretical class, like Ry, Rx, Rz, any number of gates may be applied. Any rotational transformation be applied. Okay. And this I is representing what? The index of a qubit. That at which index of a qubit, which rotation to be applied.
Okay.
Okay. Now, and followed to that one, we will be measuring. So just let me just run that one. It's run. Now this is the demonstration of that one, angle encoding. Now we are passing the angle encoding vector. Okay, the feature vector. Like it has taken for pi by 3, pi by 4, pi by 2, pi by 4. We have taken the values of what? This pi by 3, pi by 2, pi by 4. These are the values of theta, if you remember. Yes or no? Because the theta value we have to take care. Clear?
Yes, sir.
The theta value, that is in which angle format we have to encode on either on y-axis, z-axis or that is x-axis.
X-axis.
So based on that one, the angle encoding is now created. That is, it would be called, transpiled, run, and it would be counted here. Just let me run it. Here you see. Your data is looking like this. Now, the context is again changed. Your perception may be different. My data is looking like that one. Yes or no? But right
Yes, sir.
now, on the quantum circuit, your data is looking like this. Okay. So for proceeding to our quantum domain itself, first we have to be more familiar with the understanding of quantum circuit language. Because what the machine understands, that we have to understand. Okay. The same we are supposed to understand. Clear? If suppose I am just applying it to Rx gate. Okay. So if I am just applying it to Rx gate, so just let me run it. You check. Again, your representation of a data would be changing somehow.
Yes.
Clear? Now you see, this is again the example of encoding mechanism. So based on that one, now what to take? We are taking here the two classical data points, like 0.2 and 0.8. Okay. Now based on that one, we are just going to calculate a twice of pi value multiplied by x1. Means now we are going to manually calculate the values of theta 1, theta 2. Okay. And on the gate itself, we are passing their corresponding theta information. And where to apply these theta? These are the indices like 0 index and 1 index. Because it's a quantum circuit of what? 2 qubit. Clear? So on a 2 qubit quantum circuit at 0th index, we are applying the theta 1 calculation. And at the first index, we will be applying what? Theta 2 calculation. Clear my point?
Clear, sir.
Okay. Now let me run it. Or before that one, just let me run it with suppose Rx. Okay. Because this is as to demonstrate these all things, what we discussed in the class. Okay. Now you see. Let me run it. Here, this is your data is representing line. Okay. In a Rx. Now, if you see, the data is on suppose Ry. You see, this is your Ry. Clear?
So can
Now-
we do like this, that one is RY and one is RX?
Yes, because it would be, but it is actually that is a convention that whatever the rotational transformation we people are applying, the same rotational transformation we should apply onto the all data points.
Okay.
Like
okay.
if you see here in the circuits, okay,
Correct.
like
Correct.
x1, x2, xn, there are n number of data points, okay, and we are just
The only
passing-
difference is if we are using RG, then we have to have a head method also.
yes, that's it. Now here, if we want to represent it through the vectors, now you see this is the representation of the vector. This is qubit q0, this is qubit q1. Both qubits are now represented. Clear?
Clear.
This is as per these transformations. This is rotation about y-axis. If suppose let me rotate it with Rx. Okay, so first let me run it. Up now you see the transformations which are going to happen here. Now, this is your data looking like. Okay. So the things means your that is the data point associated in the angle rotation format is now changing. Clear?
Clear, sir.
Okay. Now come down to ZZ feature map. Okay. So under a ZZ feature map, so again this method is to be defined, that in the form of ZZ feature map. And for that one, again we are taking some input vectors, and to represent that how much is the form of entanglement we people are going to provide. Okay. So our input vector would be taken care by their corresponding length, and that length be assigned in a dimension. Okay. So that feature dimension, once you that is define the ZZ feature map. So under that ZZ feature map, there are some parameters that is to represent a number of repeated time of the executions of the circuit, or the whether the entanglement we people are just applying, whether it remains linear or non-linear. Okay. So the dimensions we have to initialize under the feature dimension itself, and after that one, the input parameters to be assigned with some parameters. Now, this is just a basic definition again. When you run the circuit like this, this is the feature that is ZZ feature map demo. So this is supposed to be considered as input data. So if it is input data like this 0.1, 0.2, 0.3, I am calling ZZ feature map. This function I am calling based on what? ZZ input. So based on this feature vector, we are passing it to the ZZ feature map encoding method. It will just print their corresponding circuit. You see, this is your circuit looking like. The implicit complex functionality you are not looking for. Clear my point?
Right. So it is something
This is-
like it is working something like a oracle.
Yes, it is just like a oracle. You do not know that how your data point got encoded. Okay. But it is just showing you that your data points, whatever you have, it has been encoded and it is appearing onto the quantum circuit, and it is ready for execution through the quantum algorithm. Clear?
Right, sir.
Okay. Now the same data points to be here. Now I will show you their corresponding implicit functionality also. Here you see this method. The same thing I have used here, like ZZ input 0.1, 0.2, 0.3. These are things same, but this is the decompose method I have taken. Okay. So this decompose method will take the quantum circuit underscore ZZ. Okay. This is the instance or the object of the ZZ feature map. And we people are going to decompose the functionality. Right now it is like a oracle. Now we want to go inside that how my data point is actually encoded. Okay. So for
Right.
the realization of that one, we have the decompose method. Okay. So we are calling this decompose method and just calling it to be drawn. Now you see, this is your complex functionality of your data representation. Is it fine?
Fine, sir. Fine.
Okay. So what we people will just prefer, either this representation or this one.
Naturally, niche wala.
Niche wala, that is for the exploration. Okay, that is for the understanding of the concept up to the depth. Clear? But for the abstract form of the executions, we should be more happy if we will have what? The ZZ feature map ready in the form of such oracles. Clear my point? Like
Yes,
this
sir.
unitary form of the circuit. Clear?
Clear.
Okay. So just let me come back to that the concluding remarks. First, that is the quantum machine learning we people are knowing, because already 20 minutes I have taken more. I am really apologizing for this fact. It's not ethically correct, but it's okay, no problem. A burden I just took, it's okay. But quantum machine learning combines a strength of quantum computing here in a classical machine learning, and it is to be applied on every optimization, classification, whatever the problems we people are having, and it is dealing with machine learning, the same will be dealing here. Okay. And the quantum support vectors. Okay. So for such a machine and the corresponding discussion, I'll just, if you know, one more minute I would take. Okay. If you know this, that is a structure of writing the Qiskit programs, are you comfortable, all people?
Yes.
Just
Yes,
please
sir.
give your response with
Yes,
the writing
Yes, sir. Yes, sir.
as well as the context of writing this Qiskit program. Is it clear?
Yes.
Yes, it is clear. Of course, it will take.
So
Some
I
more
will
time.
share you. Yes, I will share you. I'll share the Murthy sir with the, that is QSVM file also, that is directly to be executed and to realize on your machine. So you just be ready with your machine, and that code will be just automatically train your data. Okay. And based on the data, the model will be trained and you will be able to start predicting your answers. Okay. So I'll share you that code file also. After that one, we know that we are having certain limitations related to what? The realization of the quantum models, because we people are still there in an early stages of development, like NISQ era we people are realizing. But we know as soon as the hardware would be grow, there will be there in an advancement. Okay. So there would be a lot of efforts the people may put for the realization of the quantum hybrid algorithms, and that quantum machine learning model will be definitely applicable for all the computational science domain. Understood? So with the apology, I need to just go for just stopping this lecture, otherwise it will keep continuing. Okay. So from my side it is end, but for your context it is still going on. Yes, any questions? If you people are here, so you may ask.
Thank you, sir. Thank you for your patience and the way you taught. We learned a lot, and really, you have taken an extra half an hour, but still, the participants are happy with that. With the due apologies to the next resource person, Gopika Chaganti ma'am. Really, sir, thank you. Thank you very much, sir.
Okay. Okay, sirs, please convey my apology also to the next expert, but I could not help because unintentionally we involved in a discussion of the realization of the programs on the different environments. Okay.
No issue, no issue.
That was not at all a planned one for our context, but it's okay, no problem. Anyways, the people are learning. It's okay. Chaliye. So from my side, you all people, just please have my best wishes to learn quantum and to just apply your effort throughout your quantum computing journey. Okay. Again, good day to all. I'm leaving from this meeting now.
Thank you,
Thank
sir.
you very much.
Thank you, sir. Thank you. Thank you very much.
Great, sir.
Thank
Okay. And I'll share that code files to Murthy sir. Just please do the necessary steps and run the codes accordingly. Okay.
Right, sir. Please do share.
Okay, sir. Thank you, sir. Bye.